Hello, everyone. Welcome to my paper presentation, Tracking Patches for Open Source Software Vulnerabilities. I am Cong Xu at Fudan University. Firstly, I want to introduce a background about the open source software security risks. As we know, open source software is widely used. According to the report from the company Synopsys, up to 98% of applications contain open source software. However, open source software suffers from vulnerabilities, which are detected at an increasing speed. This causes security risks are introduced within using open source software, and up to 84% of applications contain at least one open source software vulnerability. These vulnerabilities may cause serious security problems. For example, the famous Heartbleed bug is from the popular library OpenSSL, and this vulnerability allows attackers to steal secret keys, passwords, communication data, and so on. Log4Shell is another serious vulnerability. This vulnerability is disclosed just last year, and this vulnerability allows attackers to execute arbitrary code and command by controlling log parameters. A lot of effort has been made to mitigate these security risks. Vulnerability databases play an important role in enabling various vulnerability analysis tasks. For example, CVE-list and NVD are well-known public databases, and there are also some other databases which are built by companies, such as Blackduck, SonTap, WhiteSource, Snake, and VeraCode. These databases provide valuable information, such as the description of a vulnerability, the vulnerable versions, and patches. This information can support security engineers to do some software composition analysis to find the vulnerable components and upgrade them to a fixed version. Other security tasks, such as patch presence testing, patch generation, and deployment, are also supported by this information. However, the problem is it is unclear what the quality of these patches in these databases. For example, given this CVE, in VeraCode, the provide patch is DD5A7C at mopt repository, but in the Snake, the provide patch is 976DA3 at Bison Ruby repository. The patches are different. Does that mean one of them is incorrect? Unfortunately, there is no existing work research on this. Besides, another problem is existing patch tracking approaches are either too expensive by manual effort to identify the patches or too specific to mining specific repository to identify patches. These approaches cannot apply to all open source software vulnerabilities. Considering these problems in this paper, one of our goals is to study the quality and characteristics of open source software vulnerabilities by conducting an integral study. And another goal is to propose an approach to automatically track patches, and the proposed approach is called Tracer. Okay, let's go to the empirical study section. To study the quality and characteristics of patches in industry databases, we want to answer 5 research questions. The first question is coverage analysis. This article is to measure the prevalence of missing patches in these industrial databases. And the second is consistency analysis. This is to quantify the prevalence of inconsistent patches across the 2 industrial databases. The type analysis and the cardinality analysis is to capture the common types and mapping cardinalities of patches. The accuracy analysis is to assess the accuracy of patches in the 2 industrial databases. For the data preparation, initially we want to select 5 companies' databases. However, some of them does not make their databases publicly accessible. And finally, we only select VeraCode and Snake databases as the subjects. And in the following section, we call them DBA and DBB. From the DBA and DBB, we collected 10,000 vulnerabilities to do the coverage and consistency analysis. From the collected 10,000 vulnerabilities, by manual investigation, we collected patches for 1,200 vulnerabilities, and this is the ground truth to do the type, cardinality, and accuracy analysis. For the quality of patches, in the coverage analysis, only 45% of 10,000 CVEs are with patches, and in the consistency analysis, only 90% of the CVEs have consistent patches into databases. In the accuracy analysis, the patches from 2 industrial databases have a high precision around 0.9, but a low recall only around 0.5 for CVE with multiple patches. This indicates the necessity of automatically tracking complete patches for open source software vulnerabilities. For the characteristic, we find that above 90% of patches are in the form of GitHub commit, and more than 40% of 1,200 CVEs are with multiple patches. This indicates the challenge to effectively track complete patch. Next, let's go to the approach section. During the manual investigation of patches, we find that patch commits are often frequently referenced during the reporting, discussion, and resolution of an open source software vulnerability. And this is a key idea of our approach. Tracer works in 3 steps. Firstly, it takes the CV identifier as input and constructs a reference network based on multiple knowledge sources, including NVD, the Bing, Red Hat. This step is to model references during vulnerability reporting, discussion, and resolution. Second, in the network, it selects patch commits that have high connectivity and high confidence. Finally, based on selected patch commit, it expands the select patch commits by searching relevant commits across branches of a repository to completely track patches. And then it returns the list of the identified patches. In the evaluation, we do the effectiveness evaluation first to answer how is the effectiveness of Tracer in tracking patches. Compared to industrial databases, Tracer achieves an 18% higher recall and an 8% higher FSE score. Compared to existing heuristics, Tracer finds patches for up to 270% more vulnerabilities. This indicates Tracer can complement industrial vulnerability databases by reducing manual effort and tracking patches completely. We do the generality evaluation to answer how is the generality of Tracer. First, we construct 2 larger datasets. The first new dataset contains 3,000 CVEs for which either DBA or DBB is without patch. And the second new dataset contains 5,000 CVEs for which both DBA and DBB are without patch. For the first dataset, 67% of CVEs patches are tracked by Tracer. And for the second dataset, 50% of CVEs patches are tracked by Tracer. And we sampled 100 CVEs to measure the accuracy. And the results showed that the accuracy is above 0.8. And this indicates Tracer is generalizable and can complement industrial databases. In practice, to ensure patch accuracy, even with an automatic tool to find a patch, security experts still need to verify patches manually. So we do the usefulness evaluation to answer how is the usefulness of Tracer in practice. We conducted a user study with 10 participants. They are postdocs, PhD students, master students, and engineers major in software security. They are required to find patches for 10 CVEs with and without the help of Tracer. The results show that with Tracer, the time was saved by 70% and FSE score improved by 24%. And this indicates Tracer is useful in practice for security experts to localize patches more accurately and quickly. Okay, in conclusion, Firstly, we conducted an empirical study to understand the quality and characteristics of patches in industrial databases. Second, we proposed Tracer to automatically track patches for open source software vulnerabilities. And then we extensively evaluated the effectiveness, generality, and usefulness of Tracer. The code and data are available at this website. Okay, that's all. Thank you for your attention. Have a good day. Bye.